Hello again, folks. We start today, or we pick up today at least, in the beginnings of a really, really cool part of this unit, I think. Some of the best, in my opinion, some of the best physics, real physics that we do. All right, and it's about this idea called motional EMF. And the idea there is really the idea behind the generator, the electric generator, and that in order to create in order to create a voltage, or in order to have a voltage, or even to have or create current, you don't need what we typically think of as a power supply. What I mean by that is we don't need a battery. We don't need something that you plug into the wall to make a circuit light up. A generator works on the idea that as long as you have relative movement between charges and magnetic fields, well, we know for sure that force is exerted on the charges. All right, that's nothing new in what we've written as F is Q V B. And what that really, what we haven't talked about too much is the fact that, so far all we've done is move charge through a field. All right, but if we move the field, well, we're going to see when we get into what's called Faraday's Law, we're going to see what happens there. And the same thing really happens. We can exert forces on charges not just by moving the charges in the presence of a field, but by moving the field, or changing the field at least. We'll get to that, I guess, more, like I said, when we talk about Faraday's Law. All right, now these diagrams to the right, let's put those on the back burner for a second. But yeah, here's that idea. All right, we don't need a battery. We can induce EMF, and what we mean by EMF really is a potential difference. All right, we can induce a potential difference by moving something. So here's the deal. Yeah, take that wire. I wish it didn't start right away moving, but take that wire and move it through that field. Oh yeah, EMF is the same as voltage or potential difference. Now, sorry, get over there. Okay, if this wire, I feel like this might pop up, but let's say this wire has a length L. All right, as we move this wire through there, well, there's a charge. Let's say there's a positive charge right here in the wire. All right, and as we move that charge this way, well, if we go right hand, there's a, let's see, thumb to the right, fingers into the page with that field, there's a force upward on that charge like that. All right? Now, if this charge moves through the entire length of the wire L, what we can say is this. We can say that the work done on that charge is F times L. All right? And, well, the force we know is QVB. And then there's L. Now, if there's work done, one of the things that we get interested in when we talk about EMF or potential difference is work per unit charge. So we can do all these things per unit charge, and what we get is an expression for how much EMF or voltage or potential difference is what we call induced. All right? And that expression is E equals VVL. Okay? Now that's going to come back. We'll use that a bunch, but for right now, we're going to deal more with situations in which there's an induced current or not. All right? And in this first case, I don't know if you have these things labeled or not, but here's a case top right where we take this loop of current, because we want to start talking about, what just popped up, anything good? Oh yeah, that L over there, about EMF in closed loops of current. All right, because what good is it to just have a wire that's not connected to anything, and what's that going to do for us? We're going to connect that wire to stuff. So if we close these loops, or make them, kind of like those solenoids, all right, where they're at least really wrapped up like that, what we can do is, well, like we said, we can use this idea of motion to induce current, right, or induce EMF. We'll get to current. All right, now here's the deal. We take this loop and we move it like that, and actually that does not induce an EMF, and here's why. All right, if you look at, say, the right-hand wire, all right, and say there's a positive charge here that while it was in the field was moving this way, well, just like it was on our first diagram, the force on that one would be upward. All right, if we look at this one over here that's moving this way, well, the force on that one would also be upward. So we have charges kind of pushing against each other, and therefore charge is not induced to move around at all. All right, we get no induced EMF there. There's no potential difference. All right, now this one down here, the next one, now you got to do your best to draw this. This loop gets bigger and bigger. Now here's what happens here. If we look at one of the charges on this side, like we said, it moves that way as this loop gets bigger, and that means there's a force on this one that way. Right? If we look at a charge here, it's moving this way. Well, then it's thumb up, fingers in. There's a force on this one this way. If we look at a charge here that's moving to the left, that's thumb left, fingers in. There's a force on this one downward. When we look at a charge here, it's moving downward. There's a force on it this way. So this one does induce literally a current, but we can only have current if there's a potential difference, in potential between two places. So this one, where the the loop gets bigger, well, that means that there is an induced current. This one does too, all right, because we only move one wire, right? Here's that same, well, again, that same charge that's moving this way. This one is pushed upward, so sure, we get a current, that goes like that. Right here we get a current, conventional current that goes that way. Remember, conventional current's the direction of free positive charge flow. All right? Now this one down here, well, this one does not induce any EMF or current. All right, and the reason that is because, well, let's see. If we take the charge here, it's moving this way and B is this way. So there's, the sign of 0, so that gives us 0. If we take this one up here that's moving upward as the loop got bigger, but the field to the right, let's see, that one will be pushed into the page. Forces like that. What's that circle? The force is inward. And this one down here that is moving this way, let's see, that's thumb down, field to the right, thumb down, field to the right. This one would be pushed outward. So this one would make the, as that loop got bigger, that would make the loop turn, but it wouldn't induce an EMF. All right? So what I'm trying to get at here is really the next page. There's something that actually, there's some quantity that changes when EMF is induced. Or really what happens is, it's the fact that some quantity changes, that's what induces the EMF. And that quantity deals with the fact that whether we go here and move the wire to the right, or if we move it to the left, and this doesn't show up, but if we move the wire either way, there's a quantity that we call, where is it? Magnetic flux. All right? So the quantity that really changes is the amount of field the amount of magnetic field that, well, let's see, that points, I'll say, through the closed loop. All right, and that's what we call, that is literally what we call magnetic flux. All right, so if you go back and look right here, well, we have all this field least I should say this. We have you know, all those field lines going through an enclosed space. As this thing, this wire, this part of the loop. So sorry, what I didn't explain very well before maybe is these green things are all wires. All right. So what we have here, this part is, imagine this is almost like a track made of metal, and that this part is another metal wire that we drag across the top of those things. So it's like sliding along there. And we've got to push it in order to do that. There's a force that we have to apply to make that happen. All right. So as this thing is slid across there, notice in the beginning we have a big area and therefore lots of field going through it. In the end, as the area gets smaller, we have a lot less field going through the enclosed space. All right. And so what we want to get to be able to talk about, what we want to introduce is this idea of what we call magnetic flux. All right. And when is there induced EMF? Well, Faraday's law says that there's induced EMF anytime magnetic flux changes. All right. Now, what you ought to do is go back to the last slide, and you ought to look at each case. Well, let's see if I can do that. I should be able to. Yeah, let's look at each one of these. All right, so wait for it. Here we go. Top right, right? This area stays the same, and no matter where we put the box, there's always the same number of field lines going through it. All right, so that means that flux doesn't change. The amount of magnetic field cutting through that loop does not change. The field stays the same strength everywhere. The area of the loop's always the same strength, or sorry, same size. We're just moving the area around. So what we call flux there doesn't change. Now here, yeah, right? The bigger this loop gets, the more magnetic field lines cut through it. And therefore we say that magnetic flux changes. All right, same thing here. Same thing as our next slide. I'm sorry, I don't know where we left off. I just got a phone call. But in each of the cases where the amount of magnetic field lines that cut through the enclosed area change, well, that's when we say flux changes. Now, in this case, the last one here in the bottom, notice that none of the lines go through the hoop, through the enclosed space. All right, so therefore we say that there's no magnetic flux no matter how big the loop is. All right, so flux, the big important thing about magnetic flux is we need to talk about the amount of magnetic field that goes through the loop. And if that changes, then we say there's an induced EMF. All right? Now, if we want EMF to be really big, what we do is we change flux, well, a lot, or, any guesses? Quickly. So the more we change flux, the more flux changes, and the quicker that happens, the more EMF we induce. Which, I mean, if you think about it, still jives right with what we said about F equals QVB. I'll just keep writing that as a little sidebar here, right? So for a charge that's there, there's our positive charge. Well, the faster we move it, right, the bigger the force exerted on the charge, and the harder that charge is pushed through the wire. Or if B is really big, we get a big force. All right. Well, if B's big, then that means that this is going to be big. Right? The amount of field that goes through the loop is going to be big if this field's strong. Right? So what we can do is actually quantify this idea of magnetic flux, and we call it phi. It's a phi, and we write it as simply B times A. Well, you know what? It's actually B dot A. You guys know I love my vector operations, and phi is the dot product of two vectors. Phi is a scalar because the result of any dot product is always a scalar, and which means that a lot of you will remember there's a real way to actually say, how do we find the dot product of two vectors? Some of you will remember that. It actually goes like this. B, magnitude of B, magnitude of A, times the cosine of the angle between them, right? Theta is the angle between the two vectors B and A. Well, B, sure, that's a vector. Area is a vector. Well, it is for us, and I'm going to show you that in the next slide. So here's the deal. Here's how we find magnetic flux. All right? And we said, well, to induce an EMF, you have to change flux. So that means that EMF is delta phi, well, quickly, divided by delta T. All right? EMF is the rate of change of magnetic flux. Now, let's see. One thing I forgot is that magnetic flux has cool units called Webers, the WB. EMF, we know, is just measured in volts, right? Or Webers per second, or lots of other things. All right, but those are the units of flux and EMF. All right, so this is literally what's called Faraday's Law. All right, that EMF is induced when magnetic flux changes, and its magnitude is the change in phi divided by the time it took to change. All right, that's literally what's called Faraday's Law. Now remember, we know from the other page that EMF, induced EMF, is also BVL, but that's for a wire, induced EMF in a wire of length L. All right, here we have loops, and therefore enclosed loops, which leads us to this idea of there being some enclosed area. Okay? All right, now, here's this idea of vector B versus vector A. Well, here's our enclosed loop. This is a circular loop that is supposed to be, let's see, sticking out of the page. All right, so it's in a plane that's perpendicular to the page. All right, and we can see the B vector. And now here's a different, here I've rotated that loop a little bit. Here I've rotated it a little more. All right, and in the top, well, phi, magnetic flux, is nothing. Can you tell? Remember, flux refers to the amount of magnetic field that goes through the loop. Well, these lines don't go through the loop at all. They point kind of along the plane of the loop, so there's no flux there. Here, phi is, I'll say, something. That's pretty general. There is some flux here because, and I didn't draw it as well as I could, but you can tell that some of these lines go through that loop, right? They cut right through it like that. And we can even count the ones, right? 1, 2, 3, 4, 5, 6, 6. 6 of those lines go through the loop, right? I wouldn't call phi 6, but that gives us an idea of how we can quantify it. Now down here, you can tell that, well, all of the magnetic field lines go through the loop. All right, so here, phi is as big as we can get it. All right, so when is phi big? When is phi small? Yeah, sure it does. Blah, blah, blah. Give me a minute. Oh, yeah. When is phi big and when is phi small? So phi is big here when, when the loop, when all the lines go through the loop. Now, we said in the last slide that since phi is B dot A, that's B A cosine theta. So that means in this case, it must mean, since the area is the same, area of the loop is the same all the time, that magnetic field is the same strength all the time, that must mean that there's some angle where, well, if we want the cosine of that angle to be 0, it must mean that here some theta is 90 degrees. Right? And that's how we define what we call the area vector. Right? What we do is look at the plane of the loop and then take a vector that's perpendicular to that, or what we call normal to the loop. All right, so this is our area vector. All right, here are our B vectors, and therefore there's our angle. Angle between the area vector and the magnetic field vectors. All right, second case, right? Same thing. There's the plane of the loop. There's the area of the, or sorry, there's the vector that's normal to that plane, right? So here's our area vector here, and there's a component of the area vector that's parallel. We call that A parallel. A component of the area vector that's parallel to the magnetic field vector, all right? And that's what we're looking for with this cosine thing. That gives us the component of one that's parallel to the other. And here, right, I didn't do it perfectly, of course, but what I'm trying to show here is that this area vector is right along the magnetic field vector. So therefore, theta for this, so I'll say theta is, I don't know, let's say 45-ish. Here, theta is 90. Sorry, no, it's not. It's 0. And therefore, the cosine of 0 is 1. This has the most possible flux, you know, because the most magnetic field lines go through the loop, and because the angle between the magnetic field vector and the vector we call the area vector, the angle between those is nothing. Okay? So that's what I'm trying to get at, that we have to include cosine here. Yeah, sure. How can we induce? Oh, yeah, so, you know, if we really want to change, what do you call it? If we really want to change flux, right, and induce EMF, right, by changing phi. Well, how do we do that? Here's how we do it, right? You rotate that loop, right? There's a lot of flux, less flux, 0, a little bit, a lot more, a little less. There's 0 flux, there's some more, there's tons, there's a little less, there's 0. So we keep getting different amounts of flux, right? Which means we keep getting different amounts of, well, I'm sorry, that doesn't mean that. If we keep having different amounts of flux, that means we have an induced EMF. Okay? So I'll just say this, rotate the loop. That's how we do it. Right? And that's exactly how a generator, or why a generator works. Now remember, we can do that, we can figure out, you know, that because of QVB, yeah, sure, a charge moving this way through a field like this will be pushed in this direction or that direction. So that justifies for us which way the current will go. But you know, when we get down to why, you know, why currents or EMFs are induced, it's really because flux changes. All right, this idea of magnetic flux. And so this is what Michael Faraday saw. Oh boy, I don't know when this was, yeah, he set up an experiment that looked something like this. All right, we have this iron loop here, and connected to a power supply. In this case, he really did have a power supply, and we have this thing called the primary coil. So we took this, or he took this coil of wire and wrapped it around part of this iron ring. All right, now that's a solenoid. Okay, and now on the other side of the iron ring, he wrapped just some wire and connected an ammeter. So in our secondary coil, there's no power supply, right? There's nothing that, well, there's no battery and no traditional power supply. But here's what happens. All right, there's 4 different instants or little time intervals to talk about, and one of them, I hate that. Get out of here. Stop. Well, one of them is the time when the switch closes. All right. So as the switch closes, we see that a magnetic field is created, set up, created in the primary coil. Yeah, and we could figure out the direction of that magnetic field. Let's see, if we go fingers wrap around, the field inside the coil would look like that. All right? Yeah, and then it would wrap around the outside. Now, well, what that does, and that means that V is created everywhere in the iron coil, or sorry, the iron loop. And so that means that this magnetic field actually gets carried through here. and the field comes right back through there. Right? That's just like our inside the coil, outside the coil thing. So if we create a magnetic field in this secondary coil, well, what we have is, before, if we look at, say, a little loop of the coil, one single loop right there, well, when the switch was open, there was zero magnetic field. As the switch closes, it goes from there being zero field to some field going through that secondary coil. So that means flux changes. All right? So since B is created, that means that's a delta phi, which of course takes some time, right? It's not instantaneous. There's some time that it takes over which magnetic field changes, and therefore flux changes. So that means that current is induced. Well, I'll say EMF and current are induced. So the ammeter here maybe goes blip. It goes like that and pins over to one side, but it doesn't stay there. All right, so we're going to jump right now. I guess let's jump now to here. Right, we have switch closes and we have switch closed up. Well, once the switch is closed, there's no more change in how much magnetic field goes through the loop. All right, so here, phi stays constant, and therefore delta phi over delta t is 0, and there's no EMF or induced current. So what we have to get comfortable with is the idea of this, really. I should probably say, like, while the switch is closing, or, I mean, I guess as it closes, that's okay. But once it's closed, right, things stop changing. The field gets to be what the field is, depending on the strength of the current coming out of that battery, right? And once everything sort of levels off, there's no more change. And so what happens is, so let me do this. I'm going to try to number these. Here's 1, all right? And I'll say that, so during 1, this thing maybe does that. I'll label that as 1. And if this is 2, with the switch closed, well, the meter actually goes back to 0. So all we get as the switch closes, we get a little blip, a little rock over of the meter, and then it goes back to nothing. All right, now this seems odd, but maybe it doesn't. Let's just say that here's, well, no, I guess I don't want to do that. Let's go here. We'll go to 3. Now, at the instant or the, when we actually open the switch, well, what happens? If we stop current in the primary coil, and therefore B, magnetic field, let's see, disappears, I guess is the best way to say it, or B approaches 0 in primary coil, the loop, and the secondary coil. So as this magnetic field goes from something to nothing, that's a delta phi. Now it's a delta phi that's equal and opposite to what we had before. In number 1, we close that switch, it creates a magnetic field of a certain strength, so the field goes from 0 to something. In step 3 here, the field goes from that something back to 0. So we get the same delta phi. It probably takes the same amount of time, and therefore we get E and I induced. And so what happens here, the one thing is, here again, the field goes from 0 to something. Here we go. The field goes from something to 0. All right, so if we get a change or an induced current in the ammeter, like we see here in number 1, that way, when the switch is closed, when we open the switch, it goes back over here. It goes the other way because we get the opposite change in flux, a decrease in flux in this case. And then once the switch is open, we'll call that 4. Right? Well, that's the same as 2. Phi is constant. It just stays 0. Delta phi over delta t is 0. And we get no EMF or induced current. And so what happens is the meter goes back to nothing. All right, so the little blips you see in 1 and 3 are quick. They're real quick. All right, how strong they are, how big the actual current is, depends on the battery voltage here. It depends on the number of turns in that coil. Yeah, and the resistance of the wire, I guess. So the big deal is, just the presence of magnetic flux doesn't induce anything. All right, it's the change in flux that makes everything happen. All right, I think, yeah, here's Faraday's Law. I think we will keep going with this. Let me see where we are. What's our last one? Yeah. Last one. So here's the deal. What we'll show you on Monday is that in order to induce current, like we said, we can move loops around, or what we can do is do this. Here's at least part of a field that is made by this north pole of a magnet. All right, now if it's just sitting there, sure, these field lines extend out into space. And let's just take, if we look at one of these loops like this, it has an area, an enclosed area that we can say is A. All right, and so if we look, as these magnetic field lines go off into eternity, well, right now, as we've drawn them, only this one magnetic field line actually goes through that loop. So magnetic flux there is, I don't know, small. It's not 0, right, but it's small. And if we just leave that magnet there, that flux doesn't change at all, and therefore there's no induced EMF in that loop. Okay? But if we do this, my favorite graphic of all time, all right, we do this, we move this magnet to the left, and look what happens to the number of field lines that go through that loop, through that enclosed area. Well, what we can say here is phi increases. The product of magnetic field and area goes up. All right, well, this causes an EMF of magnitude. Well, all we can say right now is delta phi over delta t. So all I'll say here is, well, how do we best do this? Because we're not equipped quite yet, I don't think, to talk about the direction of the EMF, or the polarity of it at least. So let's just say that this is, there's a potential difference across there, delta V. Right? Right? And then, as we move the magnet left, again, we can see that the number of field lines going through that area, sorry, as we move the magnet right, we can see that here phi decreases. Right? The product of B and A decreases. Right? And again, we're looking for a field that goes through the loop. Right? We're back down to one line. And again, this causes an EMF. Right? And the magnitude here, well, the magnitude would be the same exact magnitude. Except now, like we said in the last page, we do one thing to induce the EMF. We move this thing one way to induce a certain EMF. When we move it back the other way, well, we get the opposite EMF, right? That's where the ammeter blips one way when you move something, well, in this case to the left, then it'll blip the other way. We move that magnet back to the right. Okay? So that's one of the big deals. Well, this is really the big deal. That's, again, called Faraday's Law, and it deals with this idea of magnetic flux. All right? Flux is literally the product of magnetic field strength and the area of some enclosed loop. All right, now one thing I should say in this case is once we get to a case where there are lots of loops and not just one loop, right? Well, each of those loops kind of has its own area. Or we can really say that for multiple loops, we can say that phi is n b a. And I guess also cosine theta. All right, where n is the number of loops. And I'll say cosine theta in there too. Okay, so yeah, we can increase the potential for, well, potential for a potential difference, the potential for EMF by having lots of loops. All right, each of those loops with their own sort of area vector and therefore their own ability to create flux. Okay, I think that's all for now, folks. All right, I'll have a sheet for you. We've got a circular motion quiz, a circular motion and/or what do you call them? Mass spectrometer quiz next time I see you, and that'll do it. Thanks, guys.